Hello. Thank you very much for the opportunity to speak to everyone here today. I'm super excited. This is actually going to be the first Q2B that I've ever been at. And I've got to say, so far, this looks to me like it's going to be just an absolutely extraordinary event. What I'd like to talk to you about today is useful quantum computation, and specifically how error mitigation and error correction are going to help us bring useful quantum computation to the world, I think, far earlier than a lot of us ever realized was going to be possible. Now, I mean something very specific by that generic phrase, useful quantum computation. I don't mean taking small quantum systems and running quantum information science experiments. I don't mean studying noise. I don't mean studying optimal control or studying the quantum systems themselves. What I mean is taking a quantum computer and performing a calculation with it that is useful to somebody that is not a quantum information scientist. Performing a calculation that's useful to a chemist, to a material science, to somebody studying AI or machine learning. I'm really talking about taking these computers out of the laboratory and bringing them to the world. What does it take to do useful quantum computation? It's really easy to set the minimum bar and say, until you get these things, you're not there. First and foremost, you need more than 100 qubits. If you have less than 100 qubits, you're doing a computation that is easily simulatable on a classical computer. It'll be faster, it'll be cheaper, it'll be less expensive. Why wouldn't you do it that way? Secondly, and this is really the tricky one in this day and age, you need to be able to provide accurate expectation values. Nobody cares about you doing a computation if you give them the wrong answer. No simulation is ever exact. Even on a classical computer, we have step sizes on integrators. If we're doing a variational method, we have a finite size basis. Error bars are okay, but we have to know what they are, and they have to be small enough for the application that we want to run. And finally, and this is really where all those non-quantum information scientists become super important and get to play this game, we need an interesting problem to map to a circuit, and we need an observable we can measure on that circuit to give us an answer that somebody cares about. That's really where the science happens, that's where the magic happens, and that's where we're really hoping to bring all of IBM's partners, all of the quantum network to bear to help us. Now, what about that middle point I really glossed over, accurate expectation values? How do we provide those with a noisy quantum system? Well, there's a lot of ways to handle noise. Here I have kind of a generic picture of what it looks like to run a problem on a noisy computer for somebody. They want us to run a series of unitaries U. Some noise comes along lambda and messes up our answer. We want to create a reconstruction operator that undoes that noise, R. The problem is it's non-physical. You can't do that with a unitary circuit because that noise is an incoherent channel. If it's a coherent channel, there's other things you could do. So we really have four basic approaches we can follow. First of all, we can use quantum error correction. It's really the only way to correct a single shot of a circuit and give yourself the right answer at the end. I'll be talking about that last in this talk. There are also some interesting approaches, though, that work by trading time, by trading the number of shots that you run of the circuit for more and more accurate answers. And the reason why those are really exciting is we can do them on the kind of hardware that we have today. They work in one of a couple of basic ways. They can work by resampling. You run the circuit and variants of it many times, and you combine the answers of those different runs with different signs and in different ways to construct that non-physical map in post-processing. Techniques like probabilistic error cancellation, probabilistic error amplification, tensor network techniques fall in that category. You can post-select on checks, like coherent polychecks, Clifford polychecks. Or finally, you can post-detect on different types of error detection circuits. My colleague Mario will be talking about doing chemistry that way later in this conference. It's also possible, of course, to combine all of these things. The great thing about these error mitigation techniques that let us trade shots for accuracy is that we can use all of them today. My personal favorite to use as a pedagogical example is called probabilistic error cancellation. And the reason is, at least at a cartoon level, it's really easy to understand. What we're going to do is run a circuit and measure an operator. Then we'll inject various faults into the circuit and measure that operator again. By subtracting out all of those wrong answers from the observable and rescaling, we can actually recover the correct observable. The reason why I love PEC is when the assumptions that go into it are correct, when you know what your noise model is, when it's sufficiently Markovian, when you take enough shots, you can put accurate error bars on the answer it gives. This is really one of the keys to that middle point. We can get accurate answers out of noisy quantum hardware today. It does scale exponentially. The number of shots that you need for any degree of precision is exponential in how large the circuit is, but the base of that exponent is based on the error rate of your processor. For error rates that are attainable today, you can use techniques like PEC to solve problems that are larger than you can solve by direct classical simulation. And at the end of the day, when we're talking about useful quantum simulation, we're talking about useful quantum computation, we're not interested in an asymptotic statement about problems that have scaled to infinite size. We're interested in finite size problems that are bigger than we can do with a classical computer, but that we can tackle with quantum hardware today. There was a really specific example of error mitigation last year, this Nature article looking at accurate expectation values on a 127-qubit device with about 3,000 2-qubit gates. The neat thing about this circuit is it's large enough that if you try to, by brute force, simulate it on a classical computer, you can't do it. It simulated a kick dicing model and looked at some magnetization operators. Curiously, after this article came out, a lot of people became interested in simulating kick dicing models and looking at magnetization operators. And in fact, after the article came out, we had sort of an interesting situation. Lots of people had simulating this system, and just treating them all as black boxes for a moment. Here's a circuit, here's an observable, what's the answer? All of these simulations gave slightly different answers. There was an error bar. One of these was special. It was executing the circuit exactly using error mitigation on an Eagle quantum processor. All of these other techniques used different approximations to simulate the system using less classical resources and gave answers within the error bars of the experimental results. In some cases, they used a lot less classical resources. It's actually kind of amazing how far the community took this problem. But there are two things that it's extremely important to take away from all of these observations. First of all, it is incontroversial that the answer that we got off of the quantum processor was accurate. This ticked that second box. Secondly, the result on that quantum processor became the arbiter for the accuracy of all of these uncontrolled approximations. This is what at IBM we call quantum utility, a problem beyond direct simulation. It's not useful yet. We are not at useful quantum computation yet. But this ticks that second box and says, now we've hit kind of the bare minimum of the things that we need to have before it's even possible to talk about doing useful quantum computation. So how do we go from ticking the minimum to achieving the maximum, to actually showing useful quantum computation? Well, we still need three things: scale, quality, and speed. The reason is we're sitting down here at the bottom left of this space of all kinds of interesting quantum applications. As Matt alluded, over time, we expect better algorithms to be developed. All of these algorithms are going to move down and to the left on this plot. That's almost a truism. If someone makes an implementation of one of these problems that takes more qubits and more gates to run, they're not going to publish it. They can only go down and to the left. At the same time, our hardware will become more and more capable as we improve scale, the number of qubits, the y-axis on this plot, quality, how many operations we can run using error mitigation and still give accurate answers, the x-axis on this plot, and speed, which we can trade against quality using error mitigation. I'm really confident about our ability to do this. At IBM, we've invested very heavily in the technology to scale large quantum systems. It's possible to brute force almost every problem there is around signal delivery in the processor, I/O wiring, space transformers, control electronics. You can really get there without doing this hard work. But what's necessary is to do this hard work, to bring it forward and to embrace it if you want to be able to bootstrap yourself onto the next generation of devices that will be even more powerful, even more capable. And we take that very seriously, and we'll be talking to a lot of the vendors here today about how we can work together to take this even to the next step. Quality. Gate fidelity turns into how many gates you can run. Our new Harem processor has been our next big step in quality. Since 2023, we've been delivering commercially available processors that anybody can use with median error rates on the order of 0.2%. Excitingly, since 2023, the best error rates on these processors, which we track as a way of seeing what's popular in the future, possible in the future, have exceeded 3 nines since 2023. It's been quiet, but there has been a slow revolution in the quality of quantum processors. We think we can go further. One of the key contributors to gate errors on superconducting processors is the T1 of the qubits. We have available to us processes which repeatedly, lot after lot, wafer after wafer, yield transponds with T1s in excess of a millisecond, an order of magnitude better than we have in our Heron processors. It's not yet compatible with the packaging we use in our large devices, but we're working on it. This will continue to grow. And then finally, speed. We need speed not just for additional shots for error mitigation, but we need a fast, powerful software tool set that's able to handle the larger circuits that we envision becoming important as we work through this era of utility to useful quantum computation and finally to error correction. Speed has been an enormous focus for us for the last year, and actually we've had over a 60x improvement in the speed of Qiskit. It is now undeniably the fastest toolkit out there for dealing with quantum circuits. So, what do we do after this? Well, just like there are some problems that are simply too big for you to solve for on your laptop, you really need a supercomputer for it, there are some problems that are and always will be too big for error mitigation. And that's where quantum error correction really has to come in. To build an error-corrected quantum computer, it's not enough just to have a logical qubit. You really need 5 things. You need a way to encode data into a logical qubit, a way to protect it, a way to measure those logical qubits, a way to initialize them, and then finally something little, universal computation. So really, any credible plan for building an error-corrected quantum system has to answer how are you going to do these 5 things. And I'd like to just quickly talk as an example through how IBM wants to do those 5 things. Start out with how do we encode them. An error-corrected quantum processor at its heart is super optimized for one thing, and that's doing parity checks to detect errors. In the context of most quantum computers, that means that we actually encode the error-correcting code that we're going to run in the connectivity of the processor. If they're qubits that are going to participate in a parity check, we connect them together so that we can do those parity checks quickly through ancilla qubits. That's given rise to a lot of very popular codes like the surface code. Has only nearest neighbor connections in a lattice. It's super easy to build in a planar technology like superconducting qubits have been. But it has kind of a high overhead. People routinely talk about thousands of physical qubits per logical qubit in the surface code. We've been building 3D integrated processors since 2021. We're not limited to planar anymore. And so it leads very naturally to the question, what happens if we take off those training wheels? What happens if we say, you know what, we can do more than planar, let's take advantage of it and let's see what happens. And the answer is what happens is you find new codes like the gross code. It's not called the gross code because it's disgusting. It's called the gross code because the version of it that we like has 144 code qubits and a dozen is known as a gross. In this code, we take the planar checks that were present in the surface code and we add to them for each qubit 2 long-range connections. So each qubit is connected to 4 nearest neighbors, plus it has 2 highway overpasses that go to a completely different part of the chip. That breaks this nearest neighbor local 2D connectivity, and so it requires 2 things that have not been in anyone's processors to date. First of them is degree 6 connectivity. Each qubit now has 6 neighbors, 4 in the plane plus 2 long range. And the second is that it requires this breaking of the plane, those long range connections that we've historically called C-couplers. We've been working on implementing the gross code for over a year now, and actually we're pretty confident we can provide those things. We've already shown in test devices degree 6 connectivity with error rates the same as Heron. We can do this. This is a new gate for us, but it's something we can absolutely implement. We've also demonstrated that highway overpass, a connection between 2 qubits that pops up to the top of our qubit chip, goes across an entire centimeter, half the width of that qubit chip, back down again, and we've shown a high fidelity 2-qubit gate across that connection. These are really the essential tools for implementing the gross code. But why do we want to do it? Like I told you, hey, we can do this, but why should we? Well, the answer is not all logical qubits are created equal. The same as we have to worry about scale, quality, and speed for physical qubits, we have to worry about scale, quality, and speed for logical qubits. This is going to be probably the most complicated slide I have, so let's spend a moment on it. Each one of these plots is a plot of logical error rate on the y-axis versus physical error rate on the x-axis. Logical qubits aren't some magical beast that commit no errors. They have an error rate just like physical qubits. They're just suppressed by the error-correcting code. Different codes provide different amounts of protection. If you focus on that left plot, you can see each one of those colored curves is a different code in the same family as the gross code, providing a different amount of protection. The x-axis here covers about the range of physical error rates that we think is physically achievable. So across that range, if you focus on that blue curve, it barely gets to an error rate of 10 to the minus 6. It's hardly getting us past what we think we can do today with error mitigation. There's just no point in making a logical qubit that works that badly. You need more protection. The gross code that we're focused on is the red curve. It gets down to a logical error rate of about 10 to the minus 12. That gets us to the trillions of operations that Matt was talking about. That's where we want to be. That's quality. What about scale? Well, focus on the other plot. There, the gross code again is in red, and all of those other codes are different surface codes, different things where we didn't take the training wheels off, where we didn't say we can do better than that. All of them are about the same quality. They have all about the same logical error rate for the same physical error rate, but they're dramatically different in scale. The gross code requires 14 times fewer qubits to do the same thing. Now, that doesn't just mean the system is going to be cheaper to build and easier to build. That says something very big about the feasibility of building it, because the same as we had an exponential hidden inside of error mitigation, the number of shots that you need to protect to a certain degree of accuracy, there's an exponential in error-corrected systems as well. If I'm building these systems out of unreliable components, the reliability of my system is exponential in how large I have to make it. To us at IBM, that factor of 14 smaller that this gross code system can be than an equivalent surface code system, that's the difference between something that is impractical, that we do not think can work at the scale needed for practical quantum computing, and something that we think we can build, something that we think we can bring to you in 2029. Scale is important. What about speed? Error-corrected computers run a multiple slower than directly running physical operations on qubits. It takes extra cycles to do all those syndrome cycles, and you need to do a lot of them per operation. Because of that, when we start talking about the time to run a circuit on an error-corrected computer, it's longer. For that gross code computer at the lowest error rates we've talked about, a single shot could take up to an hour. First of all, I want to see that. That would be so cool to see a quantum computation that is coherent and correct over an hour. Want to get there. However, if we tried to build the same thing on a fundamental physical platform that was 1,000 times slower, that hour becomes a month. That's not just a problem in terms of what you can do with this system, it's a problem for the practicality because it sets an uptime requirement to even get one shot done. Again, we have to be careful when we talk about scale, quality, and speed in the context of an error-corrected system that we end up with something that is attainable from an engineering viewpoint. They matter. So we talked about the 5 requirements for building an error-correcting code. At the beginning of this year, we had number 1. We had our encoding, the gross code, although we hadn't published it yet. Now, coming close to the end of this year, we've ticked off these first 3 in publications. For the 4th and 5th, we at the moment have strawman based off of analogies to the surface code. We'll have those ticked off early next year. And I would really love it if everyone in this field, when they're talking about an error-corrected computer, could talk about these 5 things, and they could talk about the scale, quality, and speed that they think that they need to achieve it. So this gives me a super optimistic view of the next 9 years. Actually, it's 5 years. Wow, I've got to get working. For the next 3 years, we've ticked off the requirements, what the bare minimum we need to achieve useful quantum computation. It's just a question of when it's going to happen and who's going to do it, and hopefully it's going to happen on our hardware. Sorry. At the same time, we're working on the fundamental technologies, these C couplers, these degree 6 couplers, scale, quality, and speed, to bring error-corrected computation along for those problems that are just too big to solve any other way. I'm optimistic and I am hopeful that all of these things are going to happen and that this field is going to advance at a far greater rate than I had ever believed was possible. So thank you very much for your time, and I think we're all really looking forward to the remaining talks and hearing about how this is all going to happen.